Hello, this is Bao Xiang. I'm going to give a presentation about using regularized adversarial learning for building the digital twin of the Earth's climate system. So here is the logo of this ideology, and it's extending of the radar methodology. I hope you can enjoy it. So, uh, let me first give a very brief background. The discipline of climate science is progressing with the help of advances in observation and theory and computation. As we know that the very first large-scale observation starts from the development of electric telegraph for us to gather the weather data, and we try to extrapolate this weather data to tell us if there is a cyclone coming. So nowadays we're basically using deep learning to extend this old art of extrapolation-based forecast. And then in the year 1906, we have the primitive equations, which are listed here, that help us describe the dynamics of the atmospheric dynamics. And in like 1922, Louis Fry Richardson made the first numerical weather forecast by discretizing this equation by hand. And in 1945, we have the ENIAC, the first numerical computer that helped us to do weather forecast. And then we developed weather radar, and then we recognize that the climate dynamics is chaotic, and we try to develop better, more comprehensive numerical weather forecasts. And later we implemented a lot of more submodules like the land, ocean, and cryosphere, different parts to help us get the general circulation model to make weather forecast. And by the same time, we have the satellite orbiting around the Earth to provide the remote sensing observations. And for now, we have around 2,050 satellites orbiting around the Earth. And we know that based on these progresses, we know that the Earth climate system is featured by some peculiar characteristics. So first, it's a chaotic system, which means that it exhibits sensitive dependency on its initial state, and it's impossible to make long-term deterministic forecast. And second is high dimensional. So we have 10 to the 7th, 10 to the 8th power of gray cells for the atmosphere and ocean or land. And there are the complicated subsystem interactions between the atmosphere, ocean, land, biosphere, cryosphere, etc. So this kind of peculiar characteristics give rise to some unique problems in climate science and make it a little bit different for applying machine learning in this field, which I'll explain in this slide. So science usually progresses by recognizing, therefore, disentangling various factors that influence certain phenomena. So in climate science, the root problem, or if I exaggerate a little bit, the only problem is to disentangle. Sorry, there's a typo here. Is to disentangle uncertainties from internal climate variability noise, external forcing, and model formulation deficiency. So this is a very bold statement, and maybe some of these terms does not make sense to all of you. I'll explain with this case here. So, and using all these different scenarios to explain why the root problem is to disentangle these three uncertainties. So let's consider a very general case. We have a climate model that describes how the climate state evolves through time. And we try to apply it to make forecast. So the first step is to initialize the model, to make the model look like reality by using observational constraint to make the model state look like reality, so-called data assimilation or initialization. And we run the model for multi steps. And we know that the initial constraint does not give us a unique estimation of where the model state should be. So we have this spread, and in the end, we have a forecast spread that tells us the weather or the climate state for the coming week or for the coming decade. So usually we are faced with these three uncertainties. The first is initialization uncertainty, and second is model formulation error. We know that the trajectory might not be exactly the same as the real world, and we may have insufficient sampling of forecast spread. So how is it reflected in these different scenarios? First, in weather forecast, we use observations to partially control internal climate variability noise. That is, we don't know if we don't have any observations. We have a climatology understanding. We have a prior understanding that the current state should fall within a climatology distribution. And when we have this kind of observations, we may shrink this prior to some posterior that help us partially control the impact of so-called internal climate variability noise. And by the way, internal climate variability noise refers to the fact that small errors will always grow, uncontrollably grow, and make a deterministic meaningless. So we want to have an understanding of the model formulation deficiencies. So we really use the hindcast to identify and reduce the impact of model formulation deficiencies. And if we extend weather forecast to the case of subseasonal to seasonal forecast, the same thing here. We use observations to partially control the internal climate variability noise. But more importantly, we should control the internal climate variability noise from the ocean rather than the atmosphere, because ocean have a longer memory and it may exhibit some strong constraints on the variability of the weather through the forecasting period. And we should have an example to estimating the remaining impact of one, because if it's weather forecast, the ensemble spread might not so big. But if it's seasonal forecast, we know that this will grow pretty big and give us so-called opportunity or curse of dimensionality of predictability, which means sometimes the spread is so small that we can very much rely on these predictions. But sometimes the forecast spread is so big that it's same to climatology, which means that in this case, the forecast will not give us any informative things except our basic understanding of the historical climatology distribution of this region. And if we make the forecast even longer, we have the climate change forecast. We have the climate change detection or attribution problem. That is, and in this case, we already sample the initial state to estimate the impact of internal climate variability noise. That is why we have the large ensemble forecast in CESM large ensemble forecast for historical climate and future climate scenarios. And we use control experiments to identify the impact of external forcing. That is, we might have different. We don't know what external forcing we will have in the future, but we use some different scenarios to get a basic understanding of what external forcing will give us what kind of climate result. And we have the multi-model comparison to identify and reduce the impact of model formulation deficiencies. That is, we know that the model is not perfect, but sometimes if we can combine the result from multi-models, it might be better. And also finally, there is some fundamental problem of trying to help us get a better model, that is model diagnosis and development. Usually sometimes we use weather hindcast to identify and reduce the fast growing errors, like the cloud of the model formulation deficiencies. Usually the model formulation deficiencies come from the fact that we cannot resolve all the climate processes, and some small scale unresolved processes might influence the long-term behavior of the climate prediction. And also we can use climate hindcast, like we forecast for 100 years and make the average to get the climatology and eliminate the impact of internal climate variability noise. And also under the same external forcing, then the result will reflect where the model is wrong. So this is for slowly growing components. And sometimes it can be really expensive, because you know that to run a climate model might be really costly. So how can we use machine learning, or how can we combine the power of observation, simulation, to give us a better understanding of all these three uncertainties? We know that there have been built a lot of hypes, like machine learning can help us advance geoscience, climate science, but I don't think so if we only stick to the current paradigm for using machine learning. That is, we only have short range incomprehensive observation. And also this is a hard dimensional problem. And finally, it's a chaotic system, which means that we cannot have a consistent paired simulation observation data. So if we don't have enough high quality paired observation simulation data to diagnose and improve model performance, And to help us identify these uncertain sources, we cannot leverage these machine learning algorithms to a large scale. So I believe supervised learning is not the future. Supervised learning is unlikely to be the solution of this root problem of disentangling uncertainties from these three sources. So what's our solution? Our solution is a combination of adversarial learning and self-supervised regularization. So what is adversarial learning? Adversarial learning is like we have two competing neural networks. One try to tell some, one try to formulate the distinction task, like a supervised learning task, using some specific loss function that we define for a certain learning objective. And then we reversely apply this discriminating information to extract based on what evidence that the discriminator find that the two sets are different. So we try to formulate the problem of disentangling uncertainties using adversarial learning. And the key insight here is that for the discrimination task, we want to suppress the impact of irrelevant factors via random sampling and promote useful information of relevant factors by learning loss function related features. This might be pretty abstract for now, but I will use some examples to illustrate what it means here. An adversary is that we reverse the discriminator to extract the signal of the discriminator. So we try to apply this methodology to help us disentangle some these factors, these uncertainty sources. And we know that this is not a well-defined problem, which means that many solutions might exist for this adversarial learning task. So if it's not a well-defined problem, what's our strategy? The strategy is to impose some regularization. And how can we impose regularization there? So we use self-supervised learning to guarantee physical consistency and to impose the regularizations. So it can be imposed on several levels. In the data level, we might try to maintain spatial temporal consistency and interfield correlation as guaranteed by the physical laws that govern the climate dynamics. And at model level, we might use some useful inductive bias for model architecture, like spherical convolution or pure convolution if we are not focusing on global scale. And for the loss function level, we might have some physical constraints imposed to the discriminator. This is a little bit from the original radar framework that we have physics-informed discrimination here. And I know that these are pretty abstract concepts for now, but I will use these three case examples to illustrate these key ideas. Remember these three uncertainties. So the first one is trying to disentangle model formulation bias in the midst of internal climate variability noise and external forcing. And second is to solve the long-standing but not well-recognized problem of spinning up or shock in climate forecast or in weather forecast. So we try to develop a better data assimilation system, and hopefully it can be applied for E3SM. And finally is about climate change detection and attribution. We try to extract useful the impact of external forcing in the midst of internal climate variability noise and model formulation deficiencies. So let's go to the first example. The first example is to identify model formulation biases in the midst of internal climate variability noise and external forcing. So to introduce the idea, let's first consider this very weird, maybe uncommon case of a climatic Turing test, which is developed by Tim Palmer in one of his paper. I think it's in 2006 or 2016, I forgot. So the problem is cited as follows. We have a historical observation of precipitation field over corners. And we have a historical climate simulation from a model called Community Earth System Model version 2, starting from 1850 and run for 150 years and give us the simulation of all the precipitation field for all the past 150 years. So we train a human being and a deep neural network to distinguish whether a a map, a precipitation map, is from simulation or from observation. We first train them using some historical data and then test them in a new case, in some cases that they have never seen. So here is the performance of a human being based on 200 samples. I cannot force a human being to do like thousands of thousands of tests because humans have their limits there. So if it's observation, for all the 100 observations, the human being says that 82 are correctly classified as observation and 18 of them are classified as simulation. So pretty okay results. But if we have a deep neural network to do this task, the accuracy is almost perfect. So as scientists, we know that there must be something in the human mind that is, although the internal camera variability noise makes the fact that the simulation and observation are not paired because we cannot correctly simulate the historical climate variability. It's a chaotic system. But human beings can kind of disentangle the impact of internal climate variability noise and still recognize that the model is kind of wrong because it produces too many drizzle events, and the impact of like the Rocky Mountain and the Sierra Nevada, the impact is not so well pronounced. So there might be something wrong here, and can we correct them? So since we can use a deep neural network to identify them, we know that we can correct them reversely. So this is called fake it toward making it. I'm not saying fake it to make it, because if you only fake it, you cannot make it. If you fake it, you can march toward the goal of making it. So what we did here is a pretty simple GAN framework. If you are familiar with the idea of a generative adversarial network, but we have some. Let me first explain the architecture, and I will explain why it differs from the conventional GAN. So we have the observation here, all the samples, and we have the simulation here, and it can create all the samples of the historic simulation. If we do not consider any temporal connection, we can include temporal connection in later, but not here. So we have the observations, we have the simulations. We run the sample 1 day of precipitation simulation from the precipitation simulation, for example, January 3rd, 1982. And we try to sample from a time window of plus minus 5 years, same month, and get this January 13th, that is 1 year later, same observation. And we pass this simulation to a bias corrector. We don't know what it will do now, but it can give us something. And we have a discriminator telling whether it's observation or simulation. And we know that in the previous section, we know that a discriminator can very well tell if it's simulation or observation. So here, it should be okay. And then we reversely backpropagate the discrimination error so that the bias corrector will make the simulation be more likely viewed as observation. So if we apply this kind of min-max game here, minimize the error of the discriminator, maximize the error of discriminator by improving the bias corrector, we will make the bias corrector look more like reality. So what's the difference from the conventional GAN? Here, we are not using any generative setting. As we see here, this is simulation. Everything here is deterministic for now. So we are not using any random number generator as the latent of this generative adversarial neural network. Instead, we are using the model as the latent of reality. So there is an old saying from books saying that all models are wrong, some are useful. But when models become useful if they can serve as certain latent of reality. So here we are using the model simulation as the latent of reality. And we recall the three uncertainty sources. One is the external forcing, the other is the internal climate variability noise, and we try to extract the model formulation bias. So how can we exclude the impact of external forcing? We try to do some control experiments. That is, once we sample a simulation here, we try to make the observation being roughly from the same external forcing by forcing the simulation and observation to be roughly paired within a positive minus 5 years, same month time window. So if this is the case, the simulation and observation share the same external forcing. And we try to exclude the impact of internal climate variability noise. How is this achieved? This is achieved not by control experiment, but by random sampling. This is really important core idea of GAN, random sampling. We random sample different simulation and observation coming from different dynamical state. So the discriminator can no longer rely on this randomly sampled factor to make its distinction. So it must go toward the factor that excludes the impact of internal climate variability noise. And if these two factors have been well controlled, the discriminator must go to the physics, the error of the physics to distinguish the simulation and observation. So we can learn to correct model formulation biases by making simulation and observation indistinguishable. It's a very good wish, but it might not be true because to cheat the discriminator may not be enough due to the following three problems. First is called mode collapse. It means it's a common problem again. It means that the model may fail to may make some samples look realistic, but the whole climatology distribution from the best corrected simulation might not be preserved. Or maybe we may, for example, it can be a two-mode distribution, but after bias correction, all the samples have been shifted to here. And also it's called the other factor is called dynamical inconsistency. It means that there may be inconsistent relationship between the resolved dynamics and unresolved physics. Here we're only correcting the unresolved processes. We should not correct the resolved dynamics. So, but when we correct the resolved physics, it might be inconsistent with the resolved dynamics. And last is that the bias correction should be dependent on the resolved dynamics. But if we do not take into input of the resolved dynamics to the bias corrector, then it should not be dependent on the resolved dynamics. So with all this, we have encoded all these requirements to this loss function here. So we use the cycle GAN to guarantee that there's no mode collapse, and we have the dynamical downscaling constraint to guarantee that there is consistency between the resolved and unresolved processes, and we have this algorithm as a conditional GAN to have the dynamics as the input of both bias correctors. So the bias correction is dependent on the resolved dynamics. And we train the discriminator to maximize these two terms and train the bias corrector to minimize all these four terms. And then we will have these two kind of the discriminator and the bias detector and the bias corrector compete with each other. But when to stop the training, it's a problem I will cover in the following slide. So, but how to I will explain it. I will first give the result and then explain how we terminate the training. So we try to evaluate the model performance in three different scenarios. The first is the same as before, it's called climatic Turing test. We try to distinguish samples from observation and simulation before and after bias correction. So the first row is from observation, second row is the corresponding day's original simulation, and the last row is the corresponding day's simulation after bias correction. And we have a same human being and a same deep neural network to discriminate whether it's from simulation or observation. And here is the performance. So we know the performance in before that human being can relatively well distinguish, while deep neural network can make a perfect job. But after bias correction, human being is totally confused whether it's from simulation or from observation due to the power of GAN. And a deep neural network can still make some distinction, but not as good as before. So this suggests that when should we stop the training? Usually in many existing GAN applications, like you want to generate some phases that do not exist by taking into input of some random numbers going into the generator and get some phases that look more like reality. Then you stop the training. You know that the bias corrector, you know that the discriminator and generator are competing, while they get to some balance, and during this balance they are still trying to beat each other, and you don't know when to stop. When you stop, when you see that wow, the generated thing is look pretty like reality, so you stop based on some perceptual evaluation. But here are showing that human perceptual evaluation can be easily cheated in this physical setting. So how do we determine when to stop this training? Actually, we stop the training when we have separate validation set, and we evaluate the distribution discrepancy between the best corrected simulation and the observation using something called energy distance function. So energy distance function is like the KL divergence, or it's like the Wasserstein distance we use to formulate this GAN problem. But the good thing is that it can be computed easily. And I didn't show the algorithm here, but you can easily find it on Wikipedia. So we actually terminate the training when the energy distance function is minimized for the validation set. So the second case is we know that evaluation based on kinetic Turing test might not be satisfactory for a climate scientist. And the second case is to evaluate models performance, the climatology distribution before and after bias correction. So we come up with all the skill metrics that we can come up with for as a climate scientist. So we evaluate the moments, quantile, frequency, intensity, seasonality at grid scale. And we also evaluate the intra-field and interfield consistency before and after bias correction. So here I'm showing some representative results. Average intensity, 1 day, 3 day, 3 day maximum, winter precipitation ratio, summer precipitation ratio. The left column is for observation. The middle column is for simulation before bias correction. And the last column is for simulation after bias correction. And we can see that a lot of details have been revealed after bias correction, like the average intensity along the Cascade Mountain, and like some extreme precipitation for California bright, like here, 3D maximum, no existence here, and here we have it here. So this is quite promising, but it might still, people might still say that, well, you're just matching the distribution. Would it be correct? It's only the distribution, are you just faking it? So let's go to the last evaluation, that is so-called weather and extended range forecast. We try to apply the radar methodology for the CFS retrospective forecast and train it using the first 10 years and evaluate using the last 20 years. No overlapping between the training and evaluation. So here, original CFS is a forecast. They issue it approximately every 3 days. Each day they initialize it 4 times and make the forecast for up to 9 months. So I'm first trying to see the first day's precipitation forecast by calculating the correlation coefficient between the precipitation forecast and the precipitation observation, and the color indicates the Pearson correlation coefficient. So this is the original result. Also, it's worth mentioning here, we cascade we connect this simulation with a deep learning based downscaling model, making the 1 degree forecast to 4 kilometers. And here is the bias correction result. And we can see that, so for 1 day, originally for the Washington, Oregon Cascade, and Sierra Nevada, we have a correlation coefficient of around 0.7. But after bias correction, it can be up to 0.9. And this kind of advantage extends to high resolution cases. And here is for week 2 precipitation forecast. This is the original case. And here is bias corrected results, and showing that we can better make use of the resolved dynamics to estimate the unresolved process of precipitation after bias correction. And for some cases, even we do not have worth mentioning scale before bias correction, we can have a relatively okay performance after bias correction. So these are 3 evaluation strategies, and I know that you may not still trust this methodology. So is this the real life? Is this just fantasy? Anyway, you're just using some deepfake techniques to mimic the historical observation. Is there any theoretical justification for this? Well, actually, it turns out there are some very important theoretical supports. One is called concentration of matter, and the other is called isomorphism of a dynamical system. So let me first ask the question, what should be a good skill metric for evaluating GCMs? I know that many people in our lab are doing like skill evaluation, coming up with various skill metrics. And I would say that there's no single perfect skill metric, because each of them might only care about specific aspects of the distribution of historical observation and historical simulation, and you may not guarantee that it extrapolates to future. So in my understanding, a good skill metric should inform wherever model is biased. So it should inform wherever model is biased. It's not enough. It should also inform how to correct these biases. If it only tells us the model is wrong without telling us how to correct these biases, it's not a good skill metric. So let's say we come up with a thing called climatic Turing test, or we extend the idea from Tim Palmer's Turing test, because original Palmer's Turing test is only to say, give you two samples to tell whether it's true, whether it's fake. But in original Turing test, it's about a human, keep asking a human and a computer a series of questions, like dependent questions. And the human is a good judger of whether the thing can be taken as intelligence, or as human general, as artificial general intelligence, or as human intelligence. So the drawback of a Palmer's test is that, first, human beings are not the good judger to tell if it's simulation or observation, as we shown in our previous example. And second, it's only by seeing, it's not sequentially seeing where the model is wrong, but in our formulation that we keep nitpicking where the model is wrong and keep making up these bad aspects, and then keep nitpicking until there is no more evidence telling that if it's from simulation or observation. So we are kind of extending this Palmer Turing test, and so-called the neural Turing test, neuroclimatic Turing test. So how the neuroclimatic Turing test inform us where the model is biased? Why it tells the model is biased? So there is a theory called concentration of measure, that is, random points in a high-dimensional data distribution are concentrated in a thin layer near an average or median level set of a Lipschitz function. These random points are all linearly separable from the rest of the set, even for exponentially large random sets. What does it mean? Let me give you an example. Let's say there are thousands of kids there, and you are allowed to make a glance over these thousands of kids while they are playing. And it's very likely you can pick up which one is your daughter by simple glance over their certain aspects of them, because people are of such a high dimension. And if you can observe from really high dimensional cases, you can easily separate a sample from the rest of the sets. So this is sometimes referred to as the breadth of dimensionality, easy to separate a sample point from the rest of the sets. And the opposite side of this is the curse of dimensionality, different to search through, approximate, or integrate over a high dimensional distribution. So this means that if we apply Turing test, we can very well distinguish a biased thing from the unbiased set. And second, why climatic Turing test leads us to correct the model biases. So this is called isomorphism of dynamical systems. The isomorphic theorem states that if there is a one-to-one correspondence between points in the phase spaces of two dynamical systems, the two systems are called isomorphic, and the corresponding sets have the same probability, and orbits correspond to orbits in a time-preserving manner, which means that we can make it to weather forecast. So why we focus on like building a isomorphic mapping between simulation and observation rather than making like single, like making the weather forecast better using data-driven models? It's because it's difficult to get high quality, large amount paired simulation observation samples of the climate system. And second, we now have scalable method for minimizing the distributional difference between the phase space of simulation and observation. And here we are minimizing the sustained distance while keep monitoring the performance using the energy distance. So here we have a very bold conclusion that is to pass the climatic Turing test is a sufficient and necessary condition for building a perfect climate model. I know it's pretty bold, but let me explain why I can state it here. What is a perfect climate model? Let's focus on this question first. So given limited resolution of the computer, the perfect climate model is the model that roughly being isomorphic to reality, which means that the climatology state created by this model should be same as the real climate system. And why I would say it's sufficient and necessary to pass the climatic Turing test to build this perfect climate model. The necessity is easy to understand. So if it's a perfect model, then we cannot distinguish whether it's from simulation or observation. But why would it be sufficient? It's sufficient because the isomorphic theorem, if there is one-to-one, if the phase space is the same, then these two models, the orbit corresponds to orbits in a time-preserving manner. And why we think it's important? It's because it's very fortunate that we now have some computationally tractable approach to march toward this objective. We have the chance to build a perfect climate model if we can formulate this problem as building an isomorphic mapping between simulation and observation. We don't need any data initialization. We don't need to initialize the model like kept. We just focus on if their phase space are one-to-one correspondent or not, and add some physical constraints to guarantee that this training objective is approachable. So this is the basic theoretical guarantee of the radar methodology. And this is kind of something really excites me through the past year. And I think this is kind of going from machine learning to artificial intelligence. What is machine learning? And machine learning is like really specify a learning task. And you come up with some model architecture, and you have the data, and you do optimization toward this learning task. But here, the algorithm is quite analog to human intelligence for correcting GCMs or GCM diagnoses. So how do we correct GCM? How to bias correct and improve GCMs as human beings? What we do here is we formulate a hypothesis of where model is wrong based on our prior experience. And we design some experiment, collect some data, and run these maybe costly computational experiments. And we try to find if the hypothesis is correct and refine this hypothesis, upgrade the model. Then we go through this loop again and again. But here in our framework, what we did here is that we have the climatic Turing test to help us formulate a hypothesis of where model is wrong. So we underlook the power of climatic Turing test because we don't understand the concentration of measure phenomena. And then we learn to disentangle dynamics and physics by controlling the external forcing, random sampling the internal climate variability noise, and expose the model formulation bias. And then we correct the bias under self-supervised constraints. So we totally automate the process of how we do research in GCM bias correction or GCM diagnosis. So what's the advantage here? There is another thing that the knowledge of principle compensates the lack of knowledge of facts, and vice versa. This is a bitter lesson, which means that if you have a lot of data, you don't need to have a lot of, you don't have the principle knowledge. If you have a principle knowledge, you don't need to have a lot of data, but you can have both, okay? Some of the experts, which will take 20 years to train, they have the principles, and they compensate the lack of knowledge. But the bad thing is that humans get tired easily, but machine is tireless. Once we have this algorithm, it will keep updating this circle very quickly without any human intervention. Ultimate things like how Ford create cars instead of the original resembling line for the cars. And then everyone have cars now. Just imagine how this can update the GCM in an unimaginable speed. And also, we leave the space for the glory of human intelligence to shine in this methodology. That is, whatever kind of whatever kind of knowledge we know that, well, this algorithm is not doing as what we want, and we can still outperform the bias corrector here, we can encode this kind of understanding to regularize the generator, or we call the bias detector, and the bias discriminator. Previously, we are only constraining the generator or the bias corrector, but we know that to regularize the discriminator might give us some even better results. So these are some updated thoughts about the radar methodology. That is, we can use this method to identify model formulation deficiencies in the midst of internal climate variability noise and external forcing. So let me go to the second case. That is, we try to identify and elevate initialization disturbance for better weather and seasonal forecast. What do I mean here? So we know that in weather and seasonal forecast, a very important thing is that we have a good initialization of the model. But usually, the existing initialization strategy might not be optimal. Sometimes we might be not well constraining the initial state. Sometimes if it's coupled system for subseasonal to seasonal forecast, we know that the atmosphere, ocean, once they are individually initialized and once they are coupled, there might be some disagreement within their like state exchange, and this will bring the problem of shock. So how can we tackle this problem? I designed an interesting experiment setting using the Lorentz 96 system, which is an ordinary differential equation set with the x representing the dynamics, the slowly evolving large-scale variables, and y representing the so-called physics, the unresolved fast-varying smaller scale variables. So it resembles the real climate system in many senses. It has the external forcing as represented by F here. It has the coupling between X and Y as controlled by H. And we know that the relative magnitude can be controlled by B, and the evolving speed of Y can be controlled by C. So the experiment that I've designed here is to apply deep neural network to classify how far a simulated state is from initialization. So how do I create the data? So I get all the climatology of each dimension for X and Y, and random sample independently each dimension at the initial state. I run the model for like 2 to the 12th power steps. So, and then if it's the first step is labeled as 1, is if the step from 2 to 4 is labeled as 2, 4 to 8 labeled as 3. And I do these experiments for like 10,000 times. And then using the first several trajectories as training samples to classify whether it's very close to the initial step or whether it's very far away from the initial step, and then evaluate model performance in a separate validation set. And here we can see that the initial steps can be distinguished from later steps. This is confusion matrix. suggesting that there is some initialization disturbance here. The model needs to digest this kind of initialization disturbance to reach its climatology, to make the later steps indistinguishable from each other. And the higher frequency component has higher initialization disturbance because we can more easily distinct them. And maybe it has a shorter memory of this disturbance, which means that after several steps, it's no longer distinguishable. So this is kind of tell why we should have precipitation nowcast, statistical precipitation nowcast, instead of numerical weather forecast, numerical precipitation nowcast. It's because the processes that control the precipitation process is of higher frequency in the climate model. And if we cannot well initialize them, then at the very few steps, it might have a lot of initialization disturbance and the results might not be good. And only after several steps, after several hours, like 6 hours, then the numerical precipitation estimation catch up with the statistical method. But the lesson is that we should reversely apply what DeepMind has found to help us improve the initialization of these fast frequency variables. So, and the third thing here is that initialization disturbance becomes more distinguishable as we increase dimensionality of X and Y. This suggests the breadth of dimensionality as we mentioned earlier. And to initialize the implication here is that here we're just using some discrimination, but recall that we have the powerful tool of adversarial learning. So to initialize the model forecast, we know that we should have the initial state close to the observational constraints. This is what we have done for the past 30 years, 40 years. But also a neglected factor is that we should have the initialized state lie within the manifold of the model's phase space. This is not encoded. So how can we encode this? We might have an adversarial Kalman filter. That is, we should update the likelihood part in the Kalman filter, like include the another constraint that the ending state estimation should be indistinguishable from model's climatology. If this is the case, then the model might no longer suffer from initialization disturbance. I haven't done this part yet, but I think it can be pretty promising. So the last case, also let's recall, this case is to identify the model in how we apply the model in the midst of how to say all the other factors. So the last is to extract the external forcing information in the midst of the internal climate variability noise and model formulation differences. So now we have the coupled model in the comparison project hosted at our lab, approximately 100 models, 30 petabytes of data in its sixth phase. So the question to be answered by CMIP is that what's the fate of the Earth? So what prevents us from getting the correct answer? It's difficult to disentangle the impact of these three uncertainty sources to know what kind of external forcing give us what kind of give us this or that kind of result. And also because of the computational cost, which limits us from exploring the possible external forcing scenarios. We only explore like 4 or 5 different scenarios. Accurately detection attribution of climate change signals, because we want to exclude the impact of the internal climate variability noise. Should we have thousands of ensembles to exclude the impact of this factor? And also the model may be biased, so should we run a lot of model diagnosis to improve to remove the impact of this factor? And also, how can we understand? We know that it's not a deterministic process. How can we accurately estimate the forecasting uncertainties? We know that we want to accurately estimate the impact from this kind of aleatoric uncertainty. So we developed 2 strategies. The first is called learning a latent representation of the model. What we did here is that we gather all the historical simulations from all the models that we can have. And we try to index the model with some entity embedding factor. And we have another probability estimator called variational autoencoder, conditional variational autoencoder, that tells us the future of the Earth state condition on its current state using some like variational inference technique. And with this, we can simulate the internal climate variability noise using this kind of variational infrastructure. And we can also see what each model tells about this kind of problem setting. And here we are visualizing where different models lies in this functional space and where reality lies. So then in this case, it means that these two models might resemble reality more. And the bigger picture here is that we know that we only have limited observations of historical climate state. While we should have the CMIP models having this kind of structures that that specifically represent internal climate variability noise and model formulation deficiency, explicitly model these factors to give us a really good pro understanding of climate variability. And I'm seeing this in a Bayesian setting, that is, if we build our pro based on these 30 petabytes of data using a well-defined machine learning paradigm, and once we get this strong pro with very little observational data that give us the likelihood, we can have a good posterior estimation. And that's why I think CMIP itself should evolve into a big learning machine that explicitly represents internal climate variability noise and model formulation biases to give us exact answers about the impact of external forcing and about the uncertainty. And the other aspect is to apply adversarial disentanglement. So this is something undergoing with some other collaborators, and I will not talk into details about this aspect. So what's next? We know that climate science is not like other disciplines that try to like plug in off-the-shelf machine learning algorithm and it'll work. We're actually extending the intersection of different disciplines like climate, machine learning, probability, and dynamical system. And the intersection of all these disciplines give us some improvements regarding certain aspects of this research direction, which are listed here. And what I'm going to do is that I want to have a dynamical solver and radar to help us build a digital twin of the Earth climate system. What do I mean? So usually in a GCM, although they have tens of thousands of codes, but the basic architecture is like this. We have some dynamical solver helping us develop this, helping us tell the basic, the evolution of the geophysical fluid dynamics from the atmosphere and from the ocean. And we have a lot of like small scale process representations based on empirical or heuristic to compensate this dynamics to make it look like reality. And what we did here is that we come up with all different parameterization schemes, and we hire a lot of PhDs and postdocs to like do this aspect, another aspect, a separate aspect, and then hopefully that a combination of all this effort will give us something good. But we know that there are a lot of error compensation and the mixture of different processes. We don't know if it will work or not. But now we may just replace all of this to have a single parameterization scheme that is similar to the dynamical code, like aquohydron resolving of the fluid dynamics. Here we have a same aquohydron meshing of convolutional neural network that give us the representation of all the unresolved processes. And we train it using the regularized adversarial domain adaptation strategy. The advantage here is that we have all the real physics here, and we can merge meta sources of observations where meta had discrimination. It's scalable to big data. So isomorphic data simulation scheme. I didn't tell this, but we call it cycle again. It comes with a data simulation from simulation to observation, and observation map back to simulation. And there would be no error compensation or need for multi-objective optimization. We don't need multi-objective optimization. And the challenge would be physical interpretability. But maybe we can first make it accurate, then try to convert this deep learning parameterization to some analytical solutions of how these unresolved processes are represented and its applicability in a changing climate. So we should better disentangle the impact of external forcing in this framework. And training stability, because now we are training it maybe online, there's some feedback effect. We haven't figured out how to solve this task. And the last is stochastic parameterization of gray zone. So we may have variational inference to solve this problem. So with this, I would like to conclude this presentation. And thank you so much. For any questions, please mail me. And I'm feeling so bored in quarantine. Just find any time that is convenient for you and give me a call, and we can discuss all the aspects I discussed here. Okay, bye-bye.